Okay, so I will keep talking about the formulation of quantum mechanics in terms of two-level system. So, if you have read the famous textbook by Richard Feynman on quantum mechanics, you probably might have seen that he talks a lot about these two-level system as a way of thinking about quantum mechanics and also to build up our intuition about quantum physics. And I remember when I studied his book back in my college days, there was really no other textbook that discussed quantum mechanics in terms of the two-level system. And so, in a way, he was really ahead of his time. And of course, he was ahead of his time in many different ways, but also in terms of teaching quantum mechanics and noting that the two-level system is probably the simplest quantum system that has pretty much everything that the quantum mechanics has to offer already contained in it was really an insightful observation, in my opinion. And also, he's somehow credited with the one of the earliest suggestions of using a quantum system as a form of computer. So he was basically the person who said that one should use one could one should try to build a quantum computer to solve a complex quantum problems. So maybe his use of the two-level system and his idea of proposing a two-level system as an information unit for processing information in a quantum mechanical manner were not completely separate. So anyway, so in the two-level system, let's say you have some particle that resides in two-level system. Sorry, 0 and 1. Okay, so 0 and 1 could be, as I said in my last lecture, could be a spin up and down, or maybe the 0 and 1 correspond to the left potential well and the right potential well. So if a particle mostly resides in this region, then this state is called the zero state. And if a particle resides mostly in this region, then this state is called the one state. And you can take a linear superposition of these two using some arbitrary combination of complex numbers. But this statement that the one can take a superposition. Superposition is just another name for addition. But here we are adding up the two states rather than two numbers. So that's why the using the word superposition is a bit more appropriate than the use of the word addition. And the idea that you can superpose or add different states. So, yeah, states, namely states 0 and states 1. This is one of the fundamental concepts or one of the fundamental ansatz of quantum mechanics itself. I don't know. Maybe concepts or foundations. You can choose different words. There's no unique word to describe the importance of this idea of superposition. And I must say, I cannot emphasize the importance of these superposition idea enough. Okay. So the superposition idea actually, of course, goes back to classical mechanics, right? Where you have coordinates of a particle described by these sets of three real numbers. Okay. But one can easily decompose this general vector in terms of the superposition of these three different basis vectors. Okay, so let me introduce a some simplifying notation. Okay, so here x hat represent this basis vector 1, 0, 0, and y hat represents these second basis vector 0, 1, 0, and z hat represents a third basis vector 0, 0, 1. And we also know that these three basis vectors are mutually orthogonal. Okay, meaning that if you take the product of the x basis with the y basis, then it's 0, and if you take the product of x basis with the y base, x basis with itself, then it's 1. Normalization is 1. So maybe a more appropriate choice of word is orthonormal. And there's a very simple way of expressing this orthonormality of among the different basis vectors. Okay, so the orthonormality is expressed by this inner product. So I'm assuming that you all already know how to take an inner product of two vectors. And this inner product is 1 due to the condition of normality or normalization. And the same condition applies to all the other basis vectors. Okay. And among the different basis vectors, the inner product is 0. Okay. And so on. And you know that when you take the inner product of two vectors, it doesn't matter whether you put one vector to the left or the other one to the left, the result is the same. Actually, this is no longer the case with the quantum mechanical basis states, but I will get to it in a minute. So this the statement that the inner product between two basis vectors is the same no matter which way you take the product is only true for real valued vectors. Okay, and of course everything in classical mechanics is described in terms of real valued functions, so this is not a particularly severe or unnatural assumption when it comes to the description of classical physics, but when you try to write down some description of the quantum physics, then you must go to a quantum complex number system, and this rule has to be modified a little bit. Well, basically, if you change the order of the inner product, then you have to put a complex conjugation in the final result. And I'm sure I am hoping that you're all aware of this. Okay, so this way of using, or I should say, setting up a basis of coordinates. And then expressing, so that's number one, and then expressing all other vectors as a superposition, right? Here comes the word superposition again, of these basis vectors. Was already the scheme that classical mechanics used to describe the motion of particles. Okay, so if I were to write the coordinates in these quantum-looking notation, then this state vector is really a superposition of these three different basis vectors. I mean, sorry, this is y and this is z, okay? So what I'm proposing is that this idea of a superposition carries over to the description of quantum mechanical state in terms of this abstract object called the quantum state. And here, since we are exclusively talking about the two-level system, the superposition is done in terms of these two basis vectors, 0 and 1. Okay, then unlike the classical mechanics where x, y, and z are members of the real number system, here these two coefficients are members of a complex number system. Okay, and the fact that these two bases are orthogonal to each other or expressed by a similar relation as before. So the inner product of the state with itself is 1 by construction. And the inner product of a one basis state with the other basis state is 0, also by construction. So in basically all formulations of quantum mechanics, we only work with the orthogonalized set of bases, and if the basis that we are given is not orthogonal to begin with, there's a way to make them orthogonal by a process called the Gram-Schmitz orthogonalization. But I won't go into the details of that because this is just a mathematical procedure, and I should be content to just assume that that procedure has already been carried out, and therefore we are already starting with the bases that are already orthogonal to each other. Okay. So that's the way we set up the wave function. And now perhaps we are finally ready to tackle the Schradinger equation. So what the Schradinger equation does is to tell us how these coefficients, alpha and beta, evolve over time. Okay, so the time evolution of a quantum state in a two-level system is entirely dictated by the time evolution of these two numbers, complex numbers. 0 and 1. Okay, so what the Schradinger equation does is to tell us what these time evolution, or rather what these differential equations of alpha and beta are. Okay, so these are the derivative of these coefficients in time. And on the right-hand side is something that tells us exactly how these coefficients are going to evolve over time. And what determines the content of these things on the right-hand side is the Hamiltonian. And in the case of a two-level system, the Hamiltonian can be written as a 2 by 2 matrix. Okay. Why that is the case? Well, I do not really owe you an explanation for that, because that's really just the foundation of quantum mechanics. So it's what's given to us. And just as you are not permitted to challenge where the Newton's second law came from, maybe it came from the creator itself. In a similar way, you're really not allowed to ask where this formulation came from. A better way of saying it is that it just was given to us, and this is the way that nature works. Okay. So this collection of numbers forming a 2 by 2 matrix is what's called the Hamiltonian. And and both these coefficients alpha and beta, and all of these elements of the Hamiltonian matrix, H00, H10, H11, these are also numbers. Okay. So if you multiply these expressions through by employing the usual rules of matrix multiplication, then you can really write down these Schradinger equation in the form of some coupled differential equation like this. Okay. Now, this is a sort of thing that we already know how to solve. And I think people develop ways of solving this problem well before the invention of quantum mechanics itself. And we just have to borrow those old techniques to solve this. And that's exactly what we're going to do. So if some physical two-level system is given, that means these numbers are fixed. That is, once you fix these set of numbers, then you're fixing the nature of that particular two-level system. Okay. So fixing these four numbers is like fixing the force in the Newton's second law. Right? Once you fix the form of the force, then all you have to do is to just solve this second order differential equation. And by solving it, then you can predict the motion of a particle with absolute certainty. And in a similar way, by fixing these elements of the 2 by 2 matrix, and then just by solving these couple of differential equations, you know how exactly the quantum state will evolve over time. Okay, so that's the idea. And let me just add one more thing before I conclude this particular video. You probably have heard that these Hamiltonian matrices can only be Hermitian. Okay. And Hermitian matrices have a special property, namely that if you take the transpose of the matrix and follow that with the complex conjugation, then you return to the original matrix. Okay, so that means if you do this operation, you find H00 star, H10 star, H01 star, H11 star, which must equal H00, H01, H10, H11, because this Hamiltonian matrix must always be a Hermitian matrix. And this could be fulfilled provided that you require the diagonal elements of these 2 by 2 matrices, of this 2 by 2 matrix to be real valued. And also, at the same time, require that these off-diagonal matrices be related in this way. So if you take the complex conjugate of one of the off-diagonal elements, then you get back to the other off-diagonal element. Okay, so that means initially, we thought there were 8 real numbers to completely characterize the Hermitian matrix, Hamiltonian, because there are 4 complex numbers and each complex number consists of 2 real numbers. So we thought there were going to be 8 real numbers we had to specify in order to completely specify the Hamiltonian. But now we discovered that there's this one relation that has to be satisfied. There's another relation that has to be satisfied. And this is really 2 relations, because this is one complex number being equal to another complex number. So there are 4 constraints, which reduces the total number of independent numbers or independent degrees of freedom that goes into completely specifying a given 2 by 2 Hermitian Hamiltonian matrix. Okay. So by choosing these 4 independent numbers in a certain way, you're also characterizing the nature of that particular physical system under consideration. Okay, so in the next lecture, I will finally show you how to solve such a 2-level problem.